All right. Well, thank you all. I'm going to talk about PCI Express 6.0, and basically this is the agenda for today. We'll talk a little bit about the background, then talk about some of the key metrics and requirements for PCIe 6.0. We are adopting PAM4, so we're going to go through the error assumptions and characteristics and what do we do to get around that, namely error correction, detection, all of those stuff. Then I'm going to talk about Flit mode, also talk about some of the new low power enhancements that PCIe 6.0 is adopting. Go back to the key metrics and requirements that we would have talked about initially and see how well we did against those, and then conclude with call to action. So interconnect, it's an important pillar of compute. And I talked about this in the last OFA about how, load store IO is effectively, today at the node level. And, with CXL2 and going forward, it's getting it into the rack level, right? So fundamentally, the physical layer for anything, whether it is gas coherent links or whether it is PCIe by itself, which we will talk about, or CXL, they all use PCIe 5, right? So it's important that PCI Express technology evolves to accommodate the needs of things that we do today at the node level, as well as going forward at the rack level. And these include not just IO devices, but also with CXL, it includes things like memory expansion, things of that nature. So where bandwidth becomes and low latency, both, right, become extremely important. And already I said that we do gas coherent protocols, proprietary ones, over PCIe 5. So PCIe has been doubling the data rate with full backwards compatibility, roughly every 3 years, right? And as you can see on the picture on the right here, it changes with time based on the market demand, but roughly, if you take the cadence and off late, you will see that it has been every 2 years, right, that we have been doubling the data rate. So the last one is 2022, but in reality, it was, very beginning of 2022. So 2 years cadence is what we have. And we are doubling this every, at that cadence, and it is because there is such a huge demand. And on the other hand, PCI Express as a technology is ubiquitous, not just on the server, not just for the HPC segment, not just for networking applications, but also, for things like PC, handheld, workstation, everybody uses PCI Express. And we have adopted the policy, and that's the reason why we have been so successful for the last 2+ decades, that it's one stack, one silicon across all of these segments, but they have different form factors. So the promise of backwards compatibility is that you can design a by 16 Gen 5 device today, and it's going to interoperate with a by 1 Gen 1 device that was there, 2 decades back, right? So, and these are the different segments that are driving the needs for PCI Express, right? At the end of the day, the applications drive the demand, which you see reflected in the data rate transitions that we go through. And pretty much it's like, things like I said, as the compute demand goes up, so does memory demand, so does storage demand, so does your networking bandwidth and everything, right? Whether it is memory, storage, networking bandwidth, or any other kind of interconnect, the underlying mechanism is PCI Express 5.
Doctor, you're not presenting anymore.
Sorry?
You're not presenting your slides anymore.
Oh.
We can see you, not your slides.
All right, sorry about that.
Cool. Thank you.
Okay. All right. Okay. So let's look into the key metrics for PCIe 6.0. What are the things that are important, right? As I said, doubling the data rate is important. So of course, from 32 was the previous generation. 5.0, 6.0 will introduce 64 gig, which is a given. And PAM4, because at these higher speeds, we can no longer do NRZ and still meet the channel reach and everything. So PAM4 was also a given. So the question is, how much of latency adder do we need to add? And the answer really is 0 is a good number, but we started off saying less than 10 nanoseconds. Okay, in other words, single digit number. But then if it is coherency and those kind of applications, or even CXL caching memory kind of applications, it really has to be 0 nanosecond adder, right? Bandwidth inefficiency, how much of inefficiency can we put on top of 5.0? Because we are doing things like FEC and we might do new types of CRC, less than 2%. In other words, if I got X amount of bandwidth in the previous generation, I need to get at least 1.98x. It's not reasonable to assume that I'm going to decrease in terms of my bandwidth efficiency. And we are going to see, how we are doing all of those. We measure reliability in terms of FIT, which is failure in time, the number of failures in 10 to the power 9 hours. So we measure, we want our FIT to be, of course, at the end of the day, nothing is 0 because the probability of something going wrong is always a non-zero value, but we want it to be very close to 0, right? So that's what it means, 0, but significantly less than 1. Same channel reach as before, which is again a tall order, but that's what we have to work with because people don't really change their platforms, and things can't really move very close to the CPU, for example, right? You can't have your GPU sitting very next to the CPU because you're going to have memory and other things. So fundamentally your platforms are already tightly packed, so you can't really expect to see any more any more proximity, right, so to speak. So about same channel reach. Power efficiency, ideally we want it to be half of the previous generation. So that way your power line is flat because you're pumping twice as many bits. So if your power efficiency goes to half, then your power remains flat. In reality, what we expect to see is that power efficiency, it gets there, but it takes a few generations of designs to get there. But as long as we are on that trajectory, it's a reasonable thing to do. Low power, again, L1 is a low power state, which means that if I don't use the link, I put it to sleep. But in addition to that, what we are doing right now is we are introducing the notion of effectively, dynamically adjusting the link width depending on the bandwidth demand. So you want to basically get, a power consumption that is close to proportionate to the bandwidth usage. And we introduced a new notion called L0P, so that way we can manage our power very effectively. In general, full plug and play, backwards compatibility, those are all things. We need to be high volume manufacturing capable, and we need to scale to hundreds of lanes in a platform. It's not 4 lanes like a networking interconnect or 8 lanes, right? In a platform, you got literally, many hundreds of lanes that are PCI Express PHY, either for coherency links or for connecting to memory or for connecting to PCIe devices. So just need to make sure that, we are cognizant of all of these, right? And make the right trade-offs there. So this is PAM4. I'll quickly go through this, but basically, the way to get around the channel loss problem is that we maintain the same, effectively, Nyquist frequency. But basically you're dividing your voltage into 4 levels, right, instead of 2 levels, which was the NRZ. And effectively you do a little bit of gray coding there so that you don't end up getting 2 bits that flip, right? Anytime there is a transition from here to here, you want a single bit to flip. That way, your number of errors becomes more manageable. And then we introduce this notion of, we are expecting a burst of errors. Actually, we are expecting a lot of correlated errors because, again, our designs, we have to assume that it's a DFE-based design, and DFE-based designs mean that, if a bit gets corrupted, subsequent bits will start getting impacted. And we need to at least enable DFE types of designs for the low latency characteristics in the PHY, right? And the downside of that is, errors will start to propagate based on the DFE and depending on the bit pattern. And also we are expecting lane-to-lane correlation of errors between different lanes for common noise events like, power supply noise and things of that nature. So that's going to be a fact of life, right? And of course, given that we split the voltage levels, the I's are substantially reduced, which means that we can no longer expect these links to work in a 10 to the power minus 12 kind of bit error rate. So at the end of the day, we have to do things like gray coding, like shown here, to mitigate errors. We have to do pre-coding to minimize burst, and we have to deploy forward error correcting and replay on CRC error. Basically, those are the mechanisms that we have. So now let's look into the error correction and detection, right? So there are two mechanisms that we deploy in PCIe, right? So far we have been just deploying CRC and replay, right? We never had FEC in PCIe Gen 1 to Gen 5. And with this high data rate, basically doing a forward error correction becomes inevitable. Now, the downside of the forward error correction is that the latency and the complexity. And by the way, it increases exponentially with the number of symbols that you correct, which is what you would expect, right? More the numbers of errors, right? If you have n symbols and you can expect x number of errors, you got n choose x permutations, right? Within each of the x, depending if your symbol is 8 bits, then you got 2 to the power 8 for each of them, to the power x again, right? Because so those are the number of permutations. So permutations goes up as you correct more number of errors. And the picture here on the right shows that curve, right? So we have drawn the picture here with, if I did single correct, single symbol error correct, if I did 2 symbol error correct, and if I did 3 symbol error correct, how does it change with that first burst error rate probability? Remember, the first burst error rate comprehends the entire burst that I showed, correlation error. So you will see that if I target the number of like 10 to the power minus 6, I can get away with a single symbol correct. And that's important because what it does is I don't get into that exponential part of the forward error correction. It becomes a linear problem. My error correction and all of that latency remains substantially low, right? I mean, we can do these in definitely less than 2 nanoseconds. We can do it in a nanosecond kind of thing. And that basically is what is needed for us. But on the other hand, the detection, it needs to be really, really strong because that directly impacts the reliability. So the good news is detection is a linear problem, right? All that I need to do is I need to just check whether the syndrome that I'm getting is 0 or not. On the other hand, correction, I have to take the syndrome and try to map back to the, as I said, n choose x, 2 to the power 8 to the power x possibilities to see what I need to correct. Detection, on the other hand, I take the syndrome and I say, hey, is it 0? If it is 0, it's good. If it is not, I got a problem. That's fine. I don't need to know where exactly the problem is. I just need to tell the other side to replay that particular flit, right? Basically, that's what we rely on. And with that, what we need to do is manage this probability of the retry. And by the way, we in the specification, we give very strict guidelines in terms of if you got a flit, you need to do an ACK or NACK by X number of nanoseconds. And that X, for example, is, for example, if it is a by 16, 50 nanoseconds from pin to pin, right? We give very strong, strict guidelines. Those are guidelines, but normally people adhere to those guidelines, right? And as a result, right, I mean, my replay becomes very easy, right? It's like, less than 100 nanosecond, I can get something replayed. So basically, those are the types of things that I rely on. And the replay probability by itself is fairly low. I still have some fact that will correct. And after that, if I get an error, I will just go with the replay. So that's basically the mechanism that we adopt. PCIe, we do something called now, once I do forward error correction, right, they operate on a fixed size of data. If they operate on a fixed size of data, now I need to, PCIe has got this variable length packets. So I need to basically fit them in fixed length things called Flit, right? I mean, Flit is again, nothing new. In the coherency world, we have been using it for decades. Others have used it. So just, Flit is a fixed set of bytes. For us, it is 256 bytes. And as you can see in the picture here, out of that 256, 236 are used for transaction layer packets. We have 6 bytes of dedicated data link layer packet. These are things like your ACK, NACK, things like your credit exchange, things of that nature that you will have. You'll see that we got a very robust CRC. It's a 8 byte CRC, Reed-Solomon code. As a result, you can up to 8 bytes of error anywhere you are guaranteed to detect, and beyond that you got a 2 to the power minus 64 statistical probability of not being able to detect, right? So the probability of detection beyond 8 bytes is 1 minus 2 to the power minus 64, right? And we use that to calculate the fit. And then we got, you will see that the forward error correction that we deploy is single symbol correct, but we have interleaved them. So if you look into the interleaving here, those are color coded, right? So for every color coding, there are 2 ECC bytes. That's all we need. And if you look into the interleaving, any burst that happens, as long as that burst does not cross over 3 bytes, we can correct it, right? And basically that's what we rely on, and that's what we go through and do the calculation in terms of probability of retry. We look into, hey, what's the probability the burst will be less than 3 symbols, and anything more than that, fine, we're going to go through a replay. And from a amortization point of view, we don't do things that we used to do in the past, like sync header, framing token, per TLP, per DLLP or per packet CRC. Because of those amortization, as you will see that even though we are spending these bytes in terms of ECC and a much stronger CRC, we end up much better in terms of link efficiency. So those are the guiding principles that we have. And by the way, because we have these fixed link layer slots that we provide, the turnaround time in terms of, when I send you a Flit and knowing whether you got it or not, that can be, that's fairly minimal because you don't have to schedule. You have a dedicated slot here that you can put things in, right? It's like, you got a train and you got some bogies that are specifically assigned to you, right? So that's what we do in the PCIe 6.0 in order to get to guaranteed minimal latency for handshake across the link. This shows the picture in terms of what happens where you got your transaction on the transmit side. You're going to first of all get your whether TLP, DLP. Those are the ones link layer stuff. You're going to create the 242 bytes, do the CRC generation to 56 bytes. Then you do the forward error correction. And then, per lane, you're going to send it out. And on the way back, you're going to do just the reverse, right? So now this picture shows the replay in the Flit mode. And effectively, once you're in Flit mode, you will always be in the Flit mode. And it goes through the example of, for example, here, A is sending to B and B is replying back to A in terms of what it sends. And by the way, simultaneously B is sending to A and also getting the same response back. So in this case, you got 10, which is good. So that's fine. It gets an ACK. You got the next one, which is, but it didn't have anything. So, it gets Flit, this particular Flit, but it waits till it sees the next one and it's a good one. And by the way, this indicates that the prior one was bad, but it was, prior one didn't have any real payload. So it's going to say, I'm not going to send a NAC. I'm not going to ask for it. It's going to keep moving on. But then this Flit number 12, it got corrupted. The next one said that, oh, by the way, that had some payload, right? So it's going to ask for a repeat of that Flit number 12. And as you can see, Flit 12 got repeated here over, and then you switched over to Flit number 15. So basically that's how this is the standard, selective replay, which is new for PCIe, as well as go back end mechanism that a lot of standards adopt, including PCIe, right? So both coexist here. And the selective one is for optimization, as you can imagine. So this is the key metrics, right? In terms of what you see here is what you see on the top left is the, it's a retry probability. And as you can see that, and you will see that, FBER, the last column, 10 to the power minus 5, your retry probability gets into unreasonable numbers. So we fixed the FBER at 10 to the power minus 6, right? So it's part of, everything is about, if you want to get the low latency, you need to have some stringent requirements. So the stringency comes in, we don't do a 10 to the power minus 4, right? Basically at the end of the day, we give up about a couple of inches on the motherboard. And that's a very reasonable trade-off to do because materials change, they improve over time, and your channel lengths can come back to what they are. Once you fix your bit error rate to be, the raw bit error rate to be really, really high, you really cannot go back and undo that, right? And you don't have a low latency solution. So I put the -5 number there just for the comparison purposes. And then in general, like I said, I expect the retry time to be, around 100 nanosecond. If that is the case, you are going to see this is the bandwidth loss, for example, in terms of percentage, assuming the worst case go back end mechanism, 0.025%, very acceptable number. Flit, you can see across the board is 4 times 10 to the power minus 7, so which is pretty good. But if your replay time is, let's say, 200, fine, you got 0.05%, which is a reasonable number. So it still is less than 1% of bandwidth loss. And you will, the graph at the bottom shows the bandwidth scaling in terms of the efficiency. Like, remember I said that I want my efficiency to be at least 1.98. And as you will see for smaller payloads, an interesting thing is happening here. For smaller payloads, the efficiency is greater than 2. And the reason for that is as I said earlier, because we don't have a lot of those framing tokens and those kind of overhead per lane, per packet CRC, right? All of those got amortized. You end up getting better efficiency for small payloads, and that's especially interesting in the networking context because you have a mix of things like a lot of 8 bytes and a lot of 64 bytes, right? So 8 bytes is like 2D words over here, and 64 bytes is 16D word here, right? For example, if you look into those, and of course you got the large payload, but most people are in the 64D word is the max payload size that people support, and if you look into that, that's around 2, right? Somewhere around there. But 64 bytes, 8 bytes, you got much better efficiency, which means that you're going to get more than double the bandwidth when you go to PCIe Gen 6 at 64 gig. Latency numbers are shown on the right, and I didn't even include the latency savings that we will get because we didn't do things like 128, 130. We don't have to hunt for where the packet, framing tokens are. This is just showing, what kind of latency gains we get just because of the data rate has doubled, right? And you will see that anything negative is latency gain, right? And you will see that, yes, we do pay higher latency, let's say in a by one link for smaller packets because you have to wait till the end of the Flit boundary, right? So that's where the smaller payloads tend to hurt in terms of the latency, right? But by the time you're hitting 64 bytes, you are, even for a by one link, you're within a reasonable number. But if you look into the by 16, which is most of the usage cases, especially in the networking side, your latency is flat. You're going to gain in terms of latency. And as I said, I'm expecting substantial, healthy single digit nanoseconds gain because we didn't do on top of this, because we didn't do a lot of the framing token decoding, those kind of things that existed before. So overall latency wise, yes, by one we do have greater than 10 nanosecond, but overall the things are in a pretty good shape. So low power enhancements, again, this is, as I said, the motivation here is, we have good low power state, but it is like the entire link is either on or off. Anytime you have to turn the link on because it is SerDes, it takes microseconds. And for a lot of people, that tends to be a barrier because if I have got, let's say, 25% bandwidth that I'm steadily streaming, right? There is no way I can take advantage of that. So that's the reason why we introduced this notion of L0P, where your link is never really out of commission. Some lanes are always active. They're always transferring payload, right? The other lanes can be getting in and out of sleep state, and that's fine, because then what happens is that at least, the link is not really stalled, right? That's basically the whole purpose of L0P. And because of the lack of time, you can take a look at that. This goes through some of the handshake of how that happens. But let's look into, where, how did we do, right? This is the scorecard, so to speak. Of course, data rate, we got to 64 gig, and you saw the latency. In general, we exceeded, right, for the most cases, except, there was one case for the by one. We didn't quite get into the 10 nanoseconds. It was 11 or whatever. And then bandwidth inefficiency, we saw in a lot of cases, we got greater than 2x. So that's good. Reliability, we were around 10 to the power minus 7, which is pretty good. Channel reach and power efficiency, all of these, we expect to meet, right? So overall, we completed 6.0 spec. Definitely, it was a very challenging thing. We took some fairly unique approaches in terms of how we dealt with errors with PAM4 signaling. Again, it was necessitated because of very stringent power requirements, very stringent latency requirements, because a lot of our, memory kind of applications, right? I mean, because PCIe is also a DMA kind of an application, right? They have latency sensitivity, and we have very high reliability requirements and all of those things. So, and hundreds of lanes, right? So we had to do things to meet those needs. And as you saw in the table, we did. And I do expect, by the way, networking to be one of the early adopters, right? So as we go from 400 to 800, 800 will need PCIe Gen 6. So, any questions?
Thank you. So are there any questions for Dr. Devendra Sharma on this talk before we take a break for lunch?
So I'm standing between you guys and lunch.
It's always the most difficult time. Okay, well, I don't see any questions, Doc. Thank you for the talk. Appreciate that.
Thank you very much.
Thank you.